Okay, again, my name is Engineer Tolentino, and I'm going to present to you the third lesson of the course. This is family of curves. Now, let me start by defining what is this family of curves. Now, an equation involving a parameter as well as one or both of the coordinates of a point in a plane may represent a family of curves, one curve corresponding to each value of the parameter. Okay, let me have an example. This equation y is mx plus m, okay, represents a what? A curve whose slope and y-intercept equal. Notice that the first m here will be the slope, and the next m there will be what? The y-intercept. So therefore, this is a family of lines whose slope and y-intercept equal. If factor m, we have y is m times x plus 1, and you notice that what? You notice that this line will always pass through the point what? Negative 1 and 0. So negative 1 and okay 0. So okay. Now you notice now that this is okay, this is now the family of straight lines whose slope and y-intercept equal. Okay, all these lines passes through negative 1, 0 as is evident by this equation. So if okay, now if the constant m is treated as an arbitrary constant, then you will have then we will just have one arbitrary constant here, and we just have to differentiate it once. So this is our equation, y is mx plus m. Okay, so differentiate once, y prime is m, and then plug it there. So plug that value there in that equation there. So that means you have y is y prime times x plus 1. And simplifying, this will be, okay, just transfer y to the left there. So x plus 1, okay, so x plus 1 times y prime minus y 0. So what is this now? This will be a family or a differential equation of a family of straight lines with slope and y-intercept equal. Okay, another example is this one. The equation y squared is a times x minus 1 is obviously a family of horizontal parabolas with vertices at 1, 0. Observe that if it is the y square here, it is one horizontal. If the square is x, it will be vertical. And then the vertices is at 1, 0. So this represents now the family. In the figure, okay, in the figure, each of these parabola will represent a family of horizontal parabolas, okay, vertices at 1, 0, okay, where the parameter or where the arbitrary constant is a. This is now to be eliminated if you want to find the differential equation. So there is just one arbitrary constant. This is our, okay, so differentiate it once. Okay, what's the derivative of y squared? That is 2y prime, and the derivative of what? Of a times x minus 1 is just a. So we now know the value of a. Plug it, okay, plug it there. Plug it in this equation. You know the value of a already. That's a. So y squared is, okay, 2y prime times x minus 1. And the final differential equation is y divided by y is y 2y prime times x minus 1. Now what is this differential equation? Now this is a differential equation of a family of what? Of a family of horizontal parabolas with vertices at 1, 0. Okay. So right, this is now the rules to be taken as a guide in order for you to get the differential equation for a family of curves. The first rule, Start the solution by writing the equation of the given curve. Could be line, circle, parabola, ellipse, or hyperbola. Or of course, it could be other curves. Now B, rewrite the equation by incorporating the given conditions. Okay. Now these conditions will decrease the count of the arbitrary constants in the equation of the curve that we are interested with. And Z, get the differential equation by eliminating the arbitrary constants. Now this is from what? From lesson 2 that we did. Okay. So let's start with okay with one example. Okay, find the differential equation, okay, for the given family of integral curves. The first equation, family of lines. Okay, the first condition is family of lines that passes through the origin. Now let me visualize this simple family of lines. Okay, this is our y and x. So the family of lines will be this line, this line, right, that line. Okay, so the given curve has an equation y is a plus bx. This is the general form of a line. Now, of course, a here is the y-intercept and b is the slope. Now it says that what? If it passes through the origin, then what? Then this will satisfy this equation. This is y is 0, is a, and x is 0. So 0 is a plus b times 0. Then you can determine a is 0. Okay, a is 0 will now be actually that's the y-intercept, and the y-intercept will always be 0. So y now is bx. There is just one arbitrary constant here. So there is just one arbitrary constant. Okay, so how many arbitrary constant? Just one. Differentiate once. Y prime is b, then we know already b is y prime. And then what? Then what do we do is, okay, substitute b is y prime to this equation, y is bx. Then you have y is what? Then you have y is y prime x, or just transferring y prime x to the left, we have a differential equation now. Y minus x y prime is 0. This will now be the differential equation for what? For all lines that passes through the origin. Let's have one more example. Okay. So family of circles of radius 1 unit. Now let us sketch a few of those curves. If this is our y and x-axis, this is our y and x-axis. This could be one circle there, or there could be another circle there. Now if radius is 1 unit, and the center could be anywhere, so the center could be at HK. That HK there, HK. So alright, this is now the given equation. X minus h squared plus y minus k squared is r squared, the general equation of a circle. Substitute the radius. The radius is 1 unit, so the equation becomes x minus h squared plus y minus k squared is 1 squared. We have two arbitrary constants. Okay, so we will have two arbitrary constants. We will differentiate twice. Okay, so this is the final equation. Differentiate twice. Here we'll eliminate the arbitrary constants h and k. So the first derivative is, look at this, twice of what? Twice of x minus x plus twice of what? Twice of y minus k twice of y minus k times y prime. Okay, divide this by 2, you have what? X minus x plus y minus k y prime 0. Now let me call this just equation 1. So this is equation 1. Then okay, differentiate again. Okay, so here the derivative of x minus h is 1. The derivative of y minus k times y prime is now the derivative of a product. It's gonna be y minus k times the derivative of y prime, which is y double prime, plus y prime times the derivative of y minus k is y prime times y prime. That's y prime squared is 0. So you call this what? You call this equation, okay, call this equation 2. Yeah. Now the next step is, from here we can solve for y minus k. Look, I solve for y minus k in equation 2. So this is what? This is the final answer. Y minus k is negative 1 plus y prime squared over y double prime. We know already y minus k. And then from here, okay, we can solve for what? For x minus h. Okay, so x minus h is, let's transfer y minus k times y prime to the right. This is negative y minus k times y prime. And notice that we know y minus k, we can plug it there. So it's gonna be what? So it's gonna be just remove these figures there. Okay, it's gonna be what? X minus h times what? Times negative, you plug it, okay, you plug y minus k there. So this is x minus h times negative of 1 plus y prime square over y double prime times y prime. Simplifying, you have x minus h times 1 plus y prime squared over y double prime times y prime is x minus h. Now you see I have values for x minus h and I have value for y minus k there. So I'm gonna use this equation again here. I'm going to use this equation. I know x minus h, I know y minus k, and plug it there. You see that this was plugged, this value was, okay, this value was plugged there. Okay, and then you have what? 1 plus y prime square over y double prime times y prime square, and this, okay, and y minus k is plugged there. Okay, so that is negative 1 plus y prime square over y double prime square is 1. And finally, simplifying, okay, what do you get? 1 plus y prime square times y prime square over y double prime square plus 1 plus y prime square over y double prime square is 1. Transferring y double prime square to the right, you get what? 1 plus y prime square times y prime square plus 1 plus y prime square is y double prime square. Observe that common here is 1 plus y prime square there in both of these factors. So you can factor 1 plus y prime square there, and then you have 1 plus y prime square. And finally, you can simplify that as 1 plus y prime square equals y double prime square. You notice now that this equation will represent a family of what? Differential equation, or rather a differential equation of a family of circles of radius 1 unit. Okay. Now an alternative solution of this one, okay, this is an alternative solution. Now okay, from your calculus, you remember this formula, radius of curvature formula rho is 1 plus y prime squared 3 half over y double prime. Now, of course, our radius of curvature is 1 there. So you notice that we already have what? The differential equation. Just transfer y double prime there and we'll have our final answer. This is the one that we have what? Okay, this is the one that we had in our past solution. Or of course you can raise it to what? Raise it to the uh, second power, and then this is 1 plus y prime square is y double prime square. Okay. Let's have another example. A family of horizontal parabolas with vertices at the origin. Let's visualize this. So if this is again our y, this is again our y and x-axis. So we have a family of horizontal parabolas. Maybe one parabola is this, maybe another parabola is that. Okay, or maybe another parabola is like that, like that. So the equation of a family of parabolas is given by what? Is given by y. Okay, y minus k squared is plus minus 4a x minus x. Notice that this is the general equation of a horizontal parabola where the squared factor is y. Since the parabola passes through the origin, then substitute what? H and k0. So the final equation is y squared is plus minus 4ax. There is just one arbitrary constant, differentiate 2y times y prime is plus minus 4a, and you can plug it there already. You know already 4a, so you have what? Y square is 2y times y prime x. You can divide this by y, so and then simplify. You have 2x y prime minus y square is 0, or divide that by y, 2x y prime minus y is 0. This is now the differential equation of the family of horizontal parabolas with vertices at the origin. Okay. So here the DE of the family of horizontal parabolas with vertices at the origin.